Hello everyone, hello students. I hope you all are comfortable with our discussions on group analysis so far. And what we have been able to do in group analysis is we have been able to separate and then do the confirmatory test of all the radicals one by one in various groups adding different reagents. Along with the task of performing the confirmatory test and identifying the radical, it was very important to separate the radicals as well. You would have noticed generally there is a first hand solubility test after which a confirmatory test is performed. So recall group 2 where out of those 9 radicals copper, cadmium, bismuth, mercury, lead, arsenic, antimony, stannous, tannic, we initially began with YAS. Insoluble meant lead, copper, cadmium, mercury, bismuth, which were placed in group 2A, and soluble were arsenic, antimony, stannous, tannic. So adding YAS right away will eliminate it into 2 different groups, will rather break it into 2 different groups. The first 5 will precipitate. Now these 5 precipitating lead, copper, cadmium, mercury, bismuth in YAS, we add nitric acid, all dissolve except mercury. So if mercury does not dissolve, mercury sulfide is filtered out, and then we have a way of dissolving it and doing the confirmatory test. Soluble was lead, copper, cadmium, bismuth, and then you add sulfuric acid. So before testing lead, sulfuric acid is precipitating lead sulfate. And then you can dissolve it and do the confirmatory test. If it doesn't precipitate, copper, cadmium, bismuth. Then you add ammonium hydroxide, and the only precipitate was bismuth hydroxide. Copper, cadmium both were getting soluble. Copper was giving you a blue colored solution, cadmium was giving you a colorless clear solution. We did speak about that. And in the entire sequence of reactions in group analysis, the only radicals we fail to separate are copper and cadmium. This is where separating copper and cadmium becomes noteworthy. This is where it's a very common question in various entrance exams, because I repeat, in all of group analysis, the only 2 radicals which we fail to separate are copper and cadmium. So it's going to be a smart video clip where I talk about the separation, hashtag separating copper cadmium, hashtag use of cyanide, hashtag pseudo halide, because we'll be learning a little bit about pseudo halide in this video. We'll also get to know about some properties of copper salts which will be otherwise useful in test of copper and its salts. So let's begin with the problem at hand, which is copper and cadmium may be precipitating together and dissolving together using any particular reagent. So if you begin with copper and cadmium, like the radicals precipitated with group 2 reagent H2S and HCl, both precipitate. This is black and this is yellow, this is black and this is yellow, but we don't go by the color, because if they are present together, chances are it will together have a blackish color only. Both precipitate, both dissolve in nitric acid, so they are precipitating together, they are getting soluble together. In case you treat with NaOH or ammonium hydroxide, it's also an important piece of information. With NaOH or ammonium hydroxide, the precipitate is always a hydroxide. So whether you take NaOH or ammonium hydroxide does not make a difference. OH minus, and both will precipitate as hydroxide. In excess of NaOH, none will dissolve. No solubility. Both will remain precipitate. And this is where excess NaOH is different from excess NH4OH. You need to keep in mind the precipitate of both of them are hydroxide. But dissolving in excess of NaOH is an amphoteric behavior, which is for zincate, aluminate, plumbate and all. So something dissolving in excess of NaOH is zincate, aluminate, plumbate. Neither copper nor cadmium does that, whereas something dissolving in excess of ammonium hydroxide requires it to form a complex with ammonia. So in coordination compounds and even in group analysis, you would have seen copper forms a tetramine complex and even cadmium forms a tetramine complex. Both are bivalent, both are D block elements. This is blue and this is a clear solution. But as I told you, they precipitate together as sulfide, hydroxide. Both the sulfides dissolve in nitric acid. Both the hydroxides do not dissolve in NaOH because they are not amphoteric. And both dissolve in excess of ammonium hydroxide because to dissolve in ammonium hydroxide, it needs to form a complex with ammonia. Both form tetramine complexes with ammonia. So, this is the reason we have not been able to separate them individually. We only rely upon the two different colors to identify whether it's copper or cadmium. One way of separating the two happens to be the following. We'll be using cyanide, we'll be learning about pseudohalide a little bit. And this is what we do. We add excess of KCN. We add excess of KCN. KCN or NaCN. KCN or NaCN. If you add excess of KCN or NaCN, which is their cyanide, now both precipitate as cyanides. Both precipitate as cyanides, and in excess of KCN, both form soluble complexes. So this will give you K4CuCN6. This will give you K3CuCN6 and K4CdCN6. So this is the first layer of difference which you have with copper and cadmium treated with KCN, then excess of KCN. Both were +2, this is +2, this is +2. Now something dissolving in excess of KCN forming a complex, cyano complex. This is where you see a difference. Copper suddenly becomes Q plus and cadmium remains +2. Now, because you have been able to make it Q plus and cadmium +2, now both are soluble, Now on adding H2S, CDS yellow will precipitate, Copper will not precipitate because copper is no longer cupric. The precipitate was CuS. Copper does not precipitate because it's no longer cupric, it has become Cuprous. We'll talk about it in a little while. But this is how you separate copper and cadmium. Add KCN, both will precipitate. Add excess of KCN, both will dissolve. And if both are present together, adding H2S will precipitate only cadmium and not copper, because copper sulfide precipitate will require copper to be in +2 state. It becomes +1. Now this is the sequence by which you will be able to separate copper and cadmium, because now cadmium could be filtered out. Naturally copper is staying in the soluble form. How does it happen this way? Now you will want to copy this at your convenience, and you will want to know that this cupric cyanide undergoes a change like this. Cupric becomes cuprous of its own. Now this is very common to cupric halides. It's very common to copper chloride, copper bromide, copper iodide. We will talk about it so many times dealing with copper salts. What we are believing to be cupric precipitate is in reality cuprous precipitate. These are precipitates. Cuprous salts are precipitate. Cupric halides of their own in solution become cuprous, and the precipitate is of the cuprous halide. So this cupric of its own becomes cuprous. This is a typical behavior of copper halides, and naturally when it becomes cuprous of its own, this will not be stated in a problem. Mind you, this will not be stated in a problem. They'll just give you cupric salt with a halide. Suppose cupric salt with Ki is a very common problem. The precipitate is not of cupric iodide, the precipitate is of cuprous iodide. It's a typical behavior of halide, which is given by cyanide as well. And because by this way cupric becomes cuprous, it's basically the cuprous salt which is reacting with excess of KCN and forming the cuprous complex. I repeat, it's a copper halide property. Cupric becoming cuprous of its own, it will never be indicated in a problem. A cupric salt with Ki precipitating, remember, is always a cuprous salt. Cuprous is 3D10, they're all white. They'll give you a cupric salt with Ki, giving you a brown solution, which on adding hypo is becoming white. It was never brown, it was always white. The brown was because of the adjoining iodine, which was giving it a colored look, and hypo is going to dissolve iodine by the very popular reaction between iodine and hypo, which is in the iodometric equation. So you are going to see this very often with copper salt, and a cupric halide forming a cuprous halide of its own is how cupric cyanide becomes cuprous cyanide. For this reason, cyanides are also called pseudohalides. For this reason, cyanides are also called pseudohalides. In future, we'll see so many properties of cyanide. In future, we'll see so many properties of cyanide which will be common to a halide. Cyanide will behave so many times like a chloride, bromide, iodide. It's called a pseudohalide. Cyanide is a pseudohalide. Thiocyanide is a pseudohalide. Azide, N3- is also a pseudohalide. It's not like you want to know about all possible pseudohalides, but certainly you need to know one important fact about pseudohalide. All the pseudohalides will at least contain one nitrogen. I repeat, all the pseudohalides will contain at least one nitrogen. This information will be useful because a popular question is which of the following is not a pseudohalide, and out of 4 options you generally have an option which does not contain nitrogen. So cyanide is a pseudohalide. I can always talk about a few reactions where cyanide will act as a halide, like it acts as a cupric halide here. Cupric becomes cuprous of its own, and the complex formed is a cuprous compound. Now because it's cuprous, it does not precipitate as cupric on adding H2S, only cadmium precipitates, and the two are separated. What comes to mind is a very popular silver halide, which is AgCl. You know, AgCl is a white precipitate. AgCl is a white precipitate, a very popular white precipitate which dissolves in ammonia, forming AgNH3 whole twice Cl. This comes back on adding nitric acid. AgCN would do identical reactions. AgCN with ammonia will become soluble. Instead of chloride, we'll have a cyanide complex. This also comes back on adding nitric acid. The way you prepare chlorine, bromine from HCl, HBr on oxidation, you can get cyanogen by treating HCN by oxidation. And there are more reactions which I might share with you in future, where a cyanide will behave like a chloride, bromide or iodide. It's called a pseudohalide. So you know, you use cyanide particularly because cyanide eventually gives you a soluble complex with excess of KCl, which cannot be done using a halide. But the property of cupric becoming cuprous is a property of copper halides taken up by a pseudohalide like cyanide, and it comes handy in separating copper and cadmium. So I think this will help you in understanding and solving all questions of this kind. This much for the time being. Thank you so much.